Any questions about anything before we start? My voice is starting to come back, yep. Now I sound like my nephew will in about 3 years. Any other questions, comments, anything? Okay, in case you didn't notice, I put up another homework assignment. All right, so we started talking about game theory. And we talked about some terminology, all that kind of thing, basic definitions, action spaces, number of players, all that kind of thing. Strategies, pure and mixed, what those were. And we also talked about some classic example games. And there's going to be a couple more of those. And we're going to keep revisiting these things because, honestly, in my opinion, a good way to understand all the seemingly complicated concepts is just to remember how they manifest in these example games. Okay? And that's pretty much where we were last time. The examples, the classic example games were like Prisoner's Dilemma, Battle of the Sexes, and Matching Pennies. Those were the three we talked about last time, and there's going to be two more. We can do at least one of them today, and maybe both. Okay. And at the end of class last time, I introduced this game theory shorthand. If you're in an n-player game, given player I and some choice, some specification of strategies for players other than I, what we do is we abbreviate this specification of strategies for players other than I by sigma sub minus I, that notation, to indicate that choice, that specification. And you write U sub I of, if I have an action for player I, if I write A sub I, comma sigma sub minus I, this is the payoff to player I when he uses action AI in AI, and the other players play according to sigma sub minus I. And I'll get to Matt in just 1 second. After I write this, UI of sigma I, sigma sub minus I is the payoff to player I when he uses strategy sigma I, and the other players play according to sigma sub minus I. Question?
Sigma I like a given choice for the other n minus 1 strategies, or is it like a don't care?
It's a given. It's a given. Like, in order to figure out a payoff to player I have to know what outcomes are going to arise with what probabilities. And the only way to know that, if I specify an action for player I or a strategy for player I, which is probability distribution over his actions, I have to know what all the other players' probability distributions over their actions are in order to figure out a number for that. Okay? Yep. Some specification. Okay. Yep.
I have a quick question regarding the difference between action and strategy.
Yes.
So action is like for prisoner's dilemma, like taking C, or cooperating, or defecting, right?
Yes.
And a strategy is something like it.
It's a plan. when you're talking about pure strategies, that, as I said last time, the distinction between pure strategies and actions is something that a lot of people don't keep carefully separate in their heads. Okay, I like to think of C and D as being the possible actions, and the possible pure strategies are play C and play D. But a mixed strategy, a sigma, is going to be play C with probability 1/2, play D with probability 1/2, something like that. Okay.
So tit for tat wouldn't be a mixed strategy, or is it?
Well, tit for tat is we're in the one-shot prisoner's dilemma that tit for tat doesn't come up because you're not repeating the game. Okay. If I have time, I'm going to get to some of the iterator prisoner's dilemma stuff.
When we're talking about the payoff, why do we separate the individual's action from everybody else? If at the end we just have like all the actions, like it seems like it's already implied with use of I that you're caring about the action.
Well, you'll see in a moment why we want to use this notation and think about things this way, because we're going to bring up the notion of a best reply, and that's going to be the foundation of the notion of Nash equilibrium. So hold that thought, see if the ensuing exposition clarifies the need for such notation. Good questions, everybody. Okay. And by the way, whenever anybody's using a mixed strategy, payoff means expected payoff, right? So just note, for completeness sake, UI always means quote unquote expected payoff. When mixed strategies are involved. And one comment I didn't make last time that's worth making is that a pure strategy is really just a special case of a mixed strategy that happens to assign probability 1 to one particular action in an action space. So any pure strategy for a player, say player I, is a special case. It's a special kind of mixed strategy for player I. It happens to assign probability 1 to a single action. So, in other words, you can think of it as a mixed strategy that says I'll play this action with probability 1 and all these with probability 0. And so in some sense we can think of everything as just all mixed strategies. The reason we keep pure strategies off to the side a little bit is later on when we look at this notion of Nash equilibrium for a game, we're going to want to look for pure strategy Nash equilibria first and then look for mixed ones, so on. Okay, so those are two things to note. All right, so in this context, here's a definition, a very important definition. In this context, and when I say in this context, what do I mean? I mean, in an n-player game, given player I, okay? So, and some choice of strategy, sigma sub minus I for the other players. So given I and sigma sub minus I, a best reply action for player I against sigma sub minus I is an action. I'm going to call it A hat in AI. And just let's use AI hat just to emphasize the fact that it's an action for player I, such that the payoff to player I when he plays that action against the opposition strategy sigma sub minus I is bigger than or equal to the payoff that he gets when he plays any other action against that opposition. Okay, so let's think about this definition for just a second. What does it mean? If I'm player I, and the other players all announce they're going to play a certain mixed strategy. So now I have sigma sub minus I. I'm going to want to play a best reply action to that opposition strategy because that gives me the highest expected payoff of any of my actions. There might be multiple best replies, but you get the picture, okay? And the weird thing, using the terminology best reply, and some books use best response, it's kind of weird because when we get down to it, you're not really responding to anything because everyone's planning their own moves ahead of time in isolation. But it's convenient to think of it this way. Okay. Now I want to look at our example games and figure out best replies, stuff like that for those. Best reply actions. So let's consider the example games. What about the prisoner's dilemma? In each case, I'm going to think I'm player one. Well, actually, in the battle of the sexes, I want to look at both players. Suppose we're player one. Say you're player one. And player two plays a mixed strategy, say Q times C plus 1 minus Q times D. This here is like sigma sub minus 1 in the general game theory notation. Okay? Your payoff to playing C against that strategy, so U1 of C against that strategy, QC plus 1 minus QD, is equal to what? It's equal to Q times the payoff to the outcome CC plus 0 times the payoff to the outcome, or plus 1 minus Q times the payoff to the outcome CD. So this is equal to 3Q plus 0 times 1 minus Q equals 3Q. The payoff to D against that opposition strategy is what? It's going to be 5Q plus 1 times 1 minus Q, which is 4Q plus 1. So if I'm player 1, what is my best reply to this opposition strategy by player 2? It's always D, because 4Q plus 1 is always bigger than 3Q. In fact, it's strictly bigger than 3Q, no matter what Q is between 0 and 1. And this is a rather trivial example, but it's a good one to start with. It's always good to start small. So since U1 of D against that is always bigger than U1 of C against that, it follows that D is player 1's best reply to any strategy employed by player 2. And this I really ought to put for all Q here, just to emphasize that.
Wait, go on.
Yep.
Why do you say that it was 0, 1 minus Q? And down there, where you have
Yep, yep.
0, 1 minus Q.
Okay, if I'm player 1
Yeah.
and I play C,
Oh, wait.
no, I'm figuring out if I'm player 1 and player 2 is playing this mixed strategy and I play C against that, what is my expected payoff? Well, player 2 is going to play C with probability Q. And if I'm playing C, that means I get payoff of 3 with probability Q. He's going to play D with probability 1 minus Q, which means I get 0 payoff with probability 1 minus Q.
Oh, okay.
Thus, my expected payoff is the sum of those two, which is 3Q.
Thank you.
Yep.
But, so, okay, so you're basically basing off your strategy depending on the payoff of player 2's strategy. And your payoff, what player 2 played.
In order to figure out my best replies to various strategies on player 2's part, what I have to do is I have to figure out my payoff for every action against. Okay. Okay, so anyway, player 1's best reply action. Let me put that in there because I'm talking about best reply actions for now. Okay? Does everybody see this easy example? I'm not trying to bludgeon you by saying easy, okay, into not asking questions. Yeah? For every Q, this inequality holds. And for that runs over all the possible strategies for player 2. See, player 2 can play any mixture of C and D, right? He could play all C, he could play all D, or he could play anything in between. And all those possibilities for player 2 are embodied by this, okay? And for any of these possibilities, the payoff to playing D is better than the payoff to playing C against it. Yeah. Got it? Okay. All right, so let's look at the battle of the sexes / brothers. I can't wait till Matt finishes whatever he's eating because it's driving me nuts. I'm just kidding. What is it? What is it?
It's popcorn.
Oh, okay. Alrighty. So, again, I'm player 1. Or you're player 1. And you're gonna tell me what to put down for some of this stuff. And this is to make sure that you're with it here. So say you're player 1 for now. And player 2 plays QC plus 1 minus QB. All right? What's your payoff to playing C against that? Tell me what to put there. Yes, 3Q plus 1 times 1 minus Q. And that simplifies to 2Q plus 1. And what's your payoff to playing B against that? Yep.
Plus 2 times 1 minus.
Yes, exactly. So it's going to be 1 times Q plus 2 times 1 minus Q, and that comes out to be 2 minus Q. All right. Now things are a little more complicated here than they were in the prisoner's dilemma. Because in this case, what's going to be a best reply for me, player 1, or for you, player 1, is going to depend on the value of Q, right? if q equals 0, for example, it's better for me to play B because I'm comparing 1 to 2. If q equals 1, it's better for me to play C because I'm comparing 3 to 1, right? And this one is monotonically linearly increasing in Q. This one's monotonically linearly decreasing in Q. So it parses the Q interval nicely where they intersect. Okay, so let's figure out where 2Q plus 1 equals 2 minus Q. That happens if and only if Q equals 1/3. Right? Sometimes I do this wrong, so I'm asking you, right? Yes, okay. And you can look at these things and you can see that C is a best reply action for player 1 against that strategy for player 2 if Q is bigger than or equal to 1/3. And B is a best reply action for player 1 if and only if, I should say, Q is less than or equal to 1/3. So when Q is strictly bigger than 1/3, C is the unique best reply action. When Q is strictly less than 1/3, B is the unique best reply action, but they're both best reply actions when Q equals 1/3. Yes, Mohammed.
So we don't know what the value Q is with which player 2 is playing. So how do we try to guess at it, or do we try to?
Yeah, that's the thing. we can easily sit down and work on the game and say, well, if player 2 plays this Q strategy, then this is what I should do. But then you have to think, well, why would player 2 want to play one thing or another? No. That's what makes game theory hard. You don't know what player 2 is going to play.
Let me know. What I'm trying to say is that you try to guess the value of Q as well, as the game progresses or something.
Well, there's not much progression that can go on with a one-shot game. We'll get into some of these issues later on, why game theory was rejected originally by economists as being useless. We need to get through these basic ideas first before. Okay. All right, we all on the same page? Good. I didn't wait long enough. Are we all on the same page?
Yeah.
Rahul.
Last question.
Yeah.
In this case, when we're doing something like this, does player 1, he knows he has 2 strategies, right?
Yeah.
But he doesn't know what player 2,
That's right.
what Q is?
Yeah, he doesn't know what Q is.
But, so
I'm just doing a calculation here. What I'm doing is I'm just showing you what best reply means. I'm not saying this is how player 1 plays. I'm just showing you the manifestations of this purely mathematical definition in the context of these example games.
But when they actually play the game,
Yep.
does player 1 only write down one strategy, or can you write down both?
Each player writes down one strategy, puts it in an envelope, seals it up.
It's gone.
Yeah, and they might do the wrong thing. They might end up picking C, one of them picking C, one of them picking B. All right. Okay, so let's look at the matching pennies. Oh, actually, let me look at player 2. You can reason similarly for player 2 in this game. So if you are player 2 and player 1 plays, say, PC plus 1 minus PB. When we're doing these two-player games, we always use P for the probability on player 1 and Q for the probability on player 2. for not obvious reasons. Okay. Then what is your payoff to playing C against that? Remember, you're player 2 now. And player 1 is playing PC plus 1 minus PB. What's your payoff to playing C? 2P plus 1 times 1 minus P. Which is 1 minus P. Or 1 plus P, sorry. And your payoff to playing B is going to be what? You're player 2. And you play B against P times this plus Q times that.
1P plus 3 times 1 minus P.
Exactly. So it's 1 times P plus 3 times 1 minus P, which is 3 minus 2P. Okay, so again, if P is 0, player 2 is better off playing B. If P is 1, player 2 is better off playing C. So in between, there's some crossover point. So the crossover point is where 1 plus P equals 3 minus 2P, which is the same as P equals 2/3. Okay? And what that means is when P is bigger than 2/3, C is player 2's unique best reply action, and P is less than 2/3, B is player 2's unique best reply action. When P equals 2/3, both C and B are both best reply actions for player 2. Okay. Final example is matching pennies. I'll just whip through that one. So what is player 1's playoff? I always get confused with playoffs and payoffs and players and payers and all that stuff. I apologize for that. Okay, so player 1's payoff to playing heads against QH plus 1 minus QT is equal to Q. Yes, it should. Thank you. Okay, so player 1's payoff to playing heads against that mixed strategy is going to be 1 times Q plus minus 1 times 1 minus Q, which equals 2Q minus 1. His payoff to playing tails against QH plus 1 minus QT is going to be minus 1 times Q plus 1 times 1 minus Q, which is going to be, again, sort of, a minus 2Q. So it's the opposite of that. And those things cross over when Q is equal to 1/2, at which point they're both 0. So if Q is less than 1/2, T is the unique best reply action for player 1. If Q is bigger than 1/2, H. And if Q equals 1/2, both H and T are best reply actions. Now, these all make a lot of sense. Like, you know, if you think player 2 is going to turn up heads with probability bigger than a half, and you win when the coins match, then you're going to want to turn up heads, right? If player 2 is going to turn up tails or heads with probability less than a half, and you win when the coins match, you're going to want to turn up tails. Okay? See that? Makes a lot of sense. Okay, so that's the notion of a best reply action. And let me do one more example game before we move on to the notion of best reply strategy in Nash equilibrium. So this is a new example game. And this goes by various names. I'm going to call it Hawk Dove. And another name for it is the game of chicken. Okay? And here's the idea. Here's the idea. You've got, and this is the one that actually inspired the original paper on evolutionary game theory, which we'll get to much later on. You have two animals. Okay? And these animals could be human, or they could be non-human, whatever. And they're both after a prize of some kind worth plus 50 in whatever units. Okay? And each of them has a choice of how to act during the confrontation over this prize. It can act hawkishly, or they can act dovishly. So either animal can act H or D when contesting this prize. And what happens? If they both act H, that means they fight. They have a big fight, right? So if both H, they fight, and they get all damaged, right? They get all scratched up, and you know, their paws get broken and whatever. Okay? And they get damaged to the tune of 50, which is the whole worth of the prize. And with probability 1/2, each of them makes off with the prize. So each wins the prize with probability 1/2. Okay? If one of them acts H and one of them acts D, then the aggressive one, the H actor, makes off with the prize, and the D actor makes off with nothing. But nothing is better than minus 50, okay? And what happens if they both act dovishly? Well, if they both act dovishly, I'm again going to assume that each wins the prize with probability 1/2, but each undergoes a certain, or pays a certain cost for sort of this posturing. Like they might stand there trying to look big, right? That's what animals do, actually. There was an article in the New York Times about how you can improve your performance in job interviews by, before you go in the interview, you go into a room by yourself. Seriously, and you act big. You try to expand your chest. Seriously, I'm so not kidding.
I've heard that.
You heard that?
Yeah, they have them in body language books too.
Yeah, but the thing is, you don't even have to take the body language to the interview. You could just sort of act big by yourself for a while. And that...
There's another one I heard that if your interviewer, this is one of the interviewees
Yep.
have to go over, if your interviewer had hot drinks or coffee before interviewing you,
Well, they had, this article had pictures, little drawings of people in poses that preceded good interviews and bad interviews. Like, this is bad, okay? Making yourself small is bad. This is good, okay? This is one, they literally had this. Anyone who's ever come and talked to me about classes, right? You've seen me do this in my office. This is a really good interview pose. Yeah. But don't do it at the interview. All right. So if they're both D, they kind of pose and they huff their fur out and whatever, and each wins the prize, but that costs some money, costs them some points. So each wins prize with probability 1/2, and the posturing costs each -10, which is still a lot better than what happens. Okay, well, if you look at this game, look at this as a two-player game, this is what your payoff matrix comes out to be. -25 if they both play hawk, 50-0, and 0-50 for the ones where they both play, one plays hawk and one plays dove, and 15-15 down here. And this reflects the fact, these corner ones reflect the fact that you're winning the prize with probably 1/2, but you're definitely paying 50 points worth of injury when you fight, and you're definitely paying 10 points worth of posturing expense when you posture. Okay? So Sam, player 1, you're player 1, and player 2 plays QH plus 1 minus QD. What is your best reply? Well, your payoff to H against that is going to be minus 25Q plus 0, or plus 50 times 1 minus Q, which is 50 minus 75Q. And you want a D against that is going to be 0 times Q plus 15 times 1 minus Q, which is just 15 minus 15Q. And you discover certainly, let's look at the extreme cases. If the other guy is definitely going to be a dove, in other words, Q equals 0, then you definitely want to be a hawk, eh? Right? If they definitely want to be a hawk, then you definitely want to be a dove. But in between, there's a question. So if Q is bigger than 7/12, that's what it comes out to be. The D is the unique best response for player 1. And if Q is less than 7/12, H is the unique best response, best reply for player 1. And if Q equals 7/12, H and D both best reply actions for player 1. Okay? So, even if the other animal is more than half likely to be aggressive, for a while there it'll still pay for you to be aggressive because the prizes were so much. Okay. All right. Okay, so that's the notion of best reply action. So here's the next definition. In this context, again, given I and sigma sum minus I. So I is the index of a player, sigma sum minus I is a specification of strategies for the other players. A best reply and usually people just say best reply. They don't say best reply strategy. So I'll put that in parentheses. For player I against sigma sub minus I is a strategy, pure or mixed strategy, sigma sub I, hat for player I, satisfying the following inequality. U sub I of sigma I against that opposition. Now, Robert, you're getting the point of why we need this notation now? Why it makes things a lot easier? Okay. Is bigger than, or sigma I hat against, is bigger than or equal to ui of sigma I against that opposition for all sigma I strategies for player I. Okay. So, best reply is just a strategic generalization of best reply action. Okay. Now, if we look at our example games real quick, okay? What did we discover about the prisoner's dilemma? We discovered that no matter what the other guy's playing, my unique best reply action is going to be D. And it turns out that the unique best reply strategy is going to be play D for any opposition. So no matter what, and actually let's state it in a positive way. For any Q, the unique best reply for player 1 against QC plus 1 minus QD is the strategy, quote unquote, play D. And here I'm drawing the distinction between action D and strategy play D. In the battle of the sexes, and I'm showing you these things, I'm not proving them out, and I'm going to state a theorem that kind of summarizes them in a moment. In the battle of the sexes, for Q bigger than 2/3 or 1/3, which one was it? It's gone now. And P had 2/3, right? P had 2/3 with the, okay. For Q bigger than 1/3, the unique best reply to QC plus 1 minus QB is the strategy play C. And for Q is less than 1/3, it's going to be play B. And what if Q equals 1/3? If Q equals 1/3, in other words, if player 2 is going to play C with probability 1/3 and B with probability 2/3, we discovered that both C and B are best reply actions. I get the same payoff for either of them. So play B is a best reply strategy. Play C is a best reply strategy. But furthermore, any mixture of those is going to be as well, right? Because if I flip a coin between B and C, one of them is going to come up. I'm going to get the same number no matter which way, same payoff. Every strategy. So every strategy, Q or P times Q or P times C plus 1 minus P B is a best reply. Strategy for player 1. Okay. Now, the pattern that's emerging here you can sort of see, and I want to state the general result. So here's a general fact. In this context, once again, and the proof of this is in the handout on game theory, but I'll wave my hands through one real quick here. In this context, sigma I hat is a best reply to sigma sub minus I, a choice of strategies for the other players. If and only if every action in the action set for AI, for player I, to which sigma I hat assigns positive probability. Remember, a mixed strategy is a probability distribution over possible actions. It might leave some of them out, or it might include them all. The ones that it does include are the ones to which it assigns positive probability. If and only if every action to which sigma I hat assigns positive probability is a best reply action for player I against the opposition sigma sub minus I. So the best replies are just the mixtures of all the best reply actions. And we see that pattern emerging here in all these, in these first two examples, and we could continue it on for the matching pennies and for the hawk dove as well. Now, what's the hand wavy proof of this? It's something like this. Remember the picture. Each player goes into a room by him or herself, and in addition to trying to make themselves look big, what they do is they come up with a plan of action, right? Now, if player one happened to know that the other players were playing sigma sub minus I, and he wants to design a best reply to that in the form of a mixed strategy that he's going to put in his envelope, what he knows is that when it comes time to play the game, someone's going to spin a spinner, it's going to land on one of the actions that's called for by this mixed strategy. Would he ever want that action to be anything less than a best reply action to what player two is playing? No. So, certainly, player one is going to want every action for which this strategy calls with probability bigger than 0 to be a best reply action. And the other way around, if you take a convex combination, which is the way they phrase these things, of best reply actions, each of them gives rise to the same payoff because they're all best. So that's the best payoff, and that's going to be what sigma I hat is. All right, anyway. Best replies are mixtures of best reply actions. Let me write down that little mantra. And then maybe we'll take the 3-minute break. Best reply, in parentheses, strategies, are mixtures of best reply actions. That's exactly what they are. Okay, so 3-minute break, and then we'll talk about Nash equilibria. What city are you talking about? Capitol Hill? Is it Seattle?
Yeah.
And Seattle's not even the capital of Washington.
No, it's not.
Olympia. Do you guys know your state capitals?
At one point, I did when I was 5. Yeah.
See, my problem is I can't forget anything. So I'm always going to know that Frankfort, Kentucky, and Columbia, South Carolina. Here's a trick question. What is the capital of Massachusetts?
I don't know.
See, first thing anyone says is, well, it's not Boston. It is Boston. There you go. Okay. It's like the only state that has the the mode of the distribution equal to the mean, so to speak. It's nerd speak. Okay. Quickly, for the other two example games, for matching pennies, the best reply strategies. The best replies for player 1 against opposition QH plus 1 minus QT are play H if Q is bigger than 1/2. Play D if Q is less than 1/2. Any strategy, PH plus 1 minus P, or play T, not D. It's not Dales, it's tails, right? When Q is equal to 1/2. You get the idea, okay? So, best reply actions, best reply strategies, and so on. Okay, now, all these people like Muhammad and Rahul and a couple other people have asking these questions like, well, wait, does player 1 know what sigma sum minus I is, what the other players are playing? How is he going to plan to play if he doesn't know what that is, and so on and so forth? Well, the fact is that the way these games work is the players don't know what the other players are going to play. They have no clue. And therefore, they have no idea whether what they're putting in their envelope is indeed a best reply. They hope it is, right? They hope it is, but they have no idea whether it is. However, suppose that every player picks a strategy so that it just so happens that every player's strategy chosen is a best reply to what the other players have chosen. What if everyone happens to pick their strategies that way? Well, there's a certain stability to that situation in the following sense. Suppose I'm player 1. Even if all the other players announced, this is what I've decided to play, I would have no reason to change my choice because I've picked a best reply to that. Similarly for player 2, similarly for player 3, and so on and so forth. Okay, now what is that situation? So here's a definition. A strategy profile, and remember the profile means a choice of whatever for every player. So action profile, strategy profiles, etc. A strategy profile, sigma 1 star, sigma 2 star, up through sigma n star, and we can call that sigma star if we want, is a Nash equilibrium of the game if and only if for every I between 1 and n, for every player, sigma sub I star is a best reply to the other player's strategies, sigma sum minus I star. That's what a Nash equilibrium is. And the reason it's called an equilibrium is because it has that kind of stability property I was telling you about a minute ago, that even if all the other players announced what they were going to play, no player would have any reason to change his strategy choice. And the reason it's called a Nash equilibrium is because it's named after a guy, John Nash, John Forbes Nash. And how many people have heard of him? How many people saw the movie A Beautiful Mind or heard of it? Well, it didn't really happen that way. But, okay, Nash, who has the same middle name I do, by the way, so we're probably distantly related. Nash spent much of his life in a kind of a schizophrenic state, from the late 50s to the early 90s. And he recovered. And he got the Nobel Prize in Economics in 1994, along with 2 other guys, for his work in game theory. And while I was an undergrad at Princeton, he was in his schizophrenic stage, and he was sort of wandering around the town, all the time and kind of thinking and randomly writing stuff on boards in the math building. You know, and people would whisper and say, "That's John Nash," you know. And I would say, "Oh, okay, I had no idea who John Nash was or why he was important or anything like that." So only in retrospect can I think back on those days and say, "Oh, I knew him when." But anyway, he came up with this great idea. And this is misspelled, right? There's a T missing from strategy, okay? Those of you watching at home, I apologize for that. But anyway, this was a really, really cool idea. And the proof of this was even cooler. I don't want to go there, of course, but the genius part of this thing, Nash's proof, made what I consider ingenious use of something called Kakatani's fixed point theorem. And I'm not going to even tell you what that is, but the reason I wanted to tell you that he made ingenious use of this is if you go to the library, you know, I don't know if you guys know, but people actually used to use paper books to look up stuff. You know, they didn't, you know, go online. They didn't go to JSTOR, Library of Science, People's Library of Science, whatever. They actually use paper books. And if you go to the math library, which is, I guess, that way, it's in Malat, and you find the paper, the original Kakatani fixed point theorem paper. If you look at the journal, the bound journal, it has like 12 issues of this journal in it. All the pages are kind of white, except there's this one really dark little spot, you know, like, and so if you open it up to there, that's the Kakatani paper. Because everybody's looked at it. Everybody's looked at it. You could think of who's touched that. Hans Bethe, you know, Carl Sagan. Isn't that cool? I mean, it's so much cooler than just clicking on, you know, PDFs and, don't you think? No, actually, my friend Adam Harris, who graduated last year, prided himself on never having taken a book out of the Cornell libraries his entire time as an undergrad. And he thought that was cool. He thought that was cool. You think that's cool? What's that? You're all cool? Okay. All right. Anyway, so Nash equilibrium. I want to give you a chance to think about this. The idea of a Nash equilibrium is as follows, that even if players other than I announced their plan, player I would have no reason, no incentive to change his plan if everyone is playing a strategy that makes the strategy profile a Nash equilibrium. And the way that people state this is they say, in equilibrium, comma, which is just kind of an abbreviation for if the players are all playing strategies that, taken together in a profile, form a Nash equilibrium, then even if players other than I announce their planned strategy, player I would have no incentive to change his plan. Okay? So that's what a Nash equilibrium is. Fundamental theorem of game theory. I don't know if I've ever heard it called this except in this class. Every finite game has at least one Nash equilibrium. Maybe more, as we'll see. Number of players and finiteness of the sets of actions for each player. That's it. And it turns out you can prove that lots of non-finite games have Nash equilibria as well, with suitable assumptions on the payoff functions and whatever. Okay. Now, in an obvious terminology, a pure strategy Nash equilibrium is a Nash equilibrium where all these sigmas are pure. So that is to say, it's a strategy profile, say S1 star, S2 star, through Sn star, where these S's in the usual notation, Roman as opposed to Greek, indicate pure strategies. And when you're looking at finding equilibria, finding Nash equilibria for games, generally what you do is first you look for pure strategy Nash equilibria, and then you look for the mixed ones, the ones involving mixed strategies. So here's the, no pun intended, strategy for finding Nash equilibria is look first for pure strategy Nash equilibria, and that's the standard abbreviation for this, PSNE. Then look for the rest. Okay? So let's start looking at our example games. In this way. Okay. What about the prisoner's dilemma? Okay. Okay, this is what we want. We want to have it in this strategy profile form. Well, we want strategies, not actions. Is that what you were going to say? Yeah, yeah. Prisoner's dilemma, the only Nash equilibrium is play D, play D. Remember, a Nash equilibrium is not a strategy. It's a strategy profile. It's a choice of strategy for every player. There's two players here. Each has to have a strategy, and that's the Nash equilibrium. And it's a pure strategy Nash equilibrium, because play D is a pure strategy. Now why? Why is it the only Nash equilibrium? What does it take to be a Nash equilibrium? Whatever strategy player I is playing has got to be a best reply to whatever strategy player other than I is playing. So now we have only players 1 and 2. We discovered earlier that play D was the unique best reply for player 1 against any strategy of player 2. And symmetrically, play D is the unique best reply for player 2 against any strategy played by player 1. So the only situation where you have player 1 and player 2 playing strategies that are best replies to each other are when they're both playing play D. Okay?
What's the significance of Nash equilibrium? I mean, in terms of DV, both are just getting a payoff of 1 and 1, right? This is not high. So in the larger
What is the significance of Nash equilibrium? The significance of Nash equilibrium is that back in the day, and I'll have a little bit more to say about this later on, we talk more about the history stuff, but when von Neumann and Morgenstern and those guys originated the ideas, the original ideas of game theory, they were thinking, okay, what is the solution of a game? You know, what do we think of as the answer? What's going to happen? Or is it descriptive or is it prescriptive / normative? You know, there was questions of that kind. And there wasn't any answer in general, because there were so many ways it could come out and all that, and there were ways of justifying them all and everything. And then Nash came along with this idea where there's a certain stability to the situation in the sense that no player has a reason to change what they're doing, even if they knew what the other players were going to do. Okay? So this is like a plausible solution concept. The problem is that games generally have more than one Nash equilibrium. So there's still no unique answer. And as you note correctly, in the prisoner's dilemma example, the sole Nash equilibrium gives low payoffs to both players. So in some sense, it's not socially optimal in terms of outcomes. And a lot of research, you know, in like applications of game theory and internet routing and all that stuff has to do with the difference between the worst Nash equilibrium outcome and the socially optimal outcome. Say if you had a supervisor routing all the messages and they did it in a way that maximized everybody's social welfare, minimized everyone's latency, spread it evenly over the haves and the have-nots, you know, whatever. That's socially optimal. That would be like CC in the prisoner's dilemma. Unfortunately, selfish actors in the internet, you know, there's nobody routing the messages centrally. Everyone's greedily trying to find the best way, end up in a situation like this. And what Christos Papadimitriou Berkeley called this is the price of anarchy. If you Google that phrase, price of anarchy, you'll find a whole literature. Somebody who's got a smartphone. But yeah, okay. I didn't mean to go on that long about, but that's the point. All right. So let's follow the strategy of finding the pure strategy Nash equilibria first. So for the battle of the sexes, let's look for pure strategy Nash equilibria first. What if I'm player one? Let's better put the game up just so you. Okay, if I'm player one and player two plays C, what's my best reply? I'm player one, so I'm picking between the rows. Player two is playing C. What's my best reply? C. Okay, so C is player one's best reply to a C by player two. What is player two's best reply to a C by player one? C again, right? So play C, play C. So the pure strategy Nash equilibria. One of them is play C, play C. That's a pure strategy Nash equilibrium. And I claim also that play B and play B is a pure strategy Nash equilibria, because player one playing B is a best reply to player two playing B. Player two playing B is a best reply to player one playing B. Both ways have to work for it to be Nash equilibrium. And those are the only pure strategy Nash equilibrium. What about the mixed? What about the mixed? The only time, and I think I'm going to need to pay a little more attention to this at the beginning of class next time, but remember that fundamental result that to be a best reply strategy, you have to mix best reply actions, right? So the only time a player will want to mix in this game is if both actions yield the same payoff, if they're both best replies. And the only way that can happen is if the other player is playing that special Q value or that special P value. Okay. So it turns out there's exactly one, and we'll get to this in detail next time, other Nash equilibrium, one that involves mixed strategies. It's going to be when player one plays 2/3 C plus 1/3 B, and player 2 plays 1/3 C plus 2/3 B. That's the only other Nash equilibrium, and we'll get to that in more detail next time. But here's how you can characterize this one. You can say, if you remember, player 1 favors C over B, player 2 favors B over C. If you play mixed strategy, where you play your favorite thing with probability 2/3 and your unfavorite with probability 1/3, that turns out to be Nash equilibrium. And as it happens, the payoff to both players is lower for this Nash equilibrium than it is for either of the pure strategy Nash equilibrium. We'll get to that next time. And there might be people here who still haven't picked up their tests, but I doubt it, because yeah, where's Andrew Knaus been? He hasn't been around for a while.